today we're looking at probability. The skills that we're trying to accomplish today, our learning targets, we would like to be able to apply, experimental probability to analyze the likelihood of an event, theoretical probability to analyze the likelihood of an event, and also apply independent event as well as dependent event probability concepts to calculate simple probability. So this lesson will be divided into a couple parts. In this part in particular, we want to look at experimental probability, theoretical probability, and I'll break the last part down as we go further. Probability is the measure of how likely it is that an event will occur. Experimental versus theoretical probability. You see, experimental probability is calculated from data collected during an experiment. Now, you don't need lab coats to have an experiment. For example, experimental probability is typically used in sports. We're interested in putting the right player on the free throw line in a basketball game at the end of the game. So who do we go to? We go to the person that has the best percentage, the best likelihood of getting those baskets at the end of the game. We got to win the game, so we want to put that person there. We want to go with the best pitcher in a baseball game. So we look at the person who's got the most strikeouts compared to the most balls thrown just in general. Theoretical probability is not so much about an experiment. And by the way, an experiment, like I said, you don't need a lab coat in a science lab to perform an experiment. You can perform an experiment in a basketball game at the free throw line. But theoretical probability is more like taking a coin and I'm flipping it. Or I'm taking a number cube, a die, and I'm going to roll it, and I'm going to figure out which number comes up. This is theoretical probability. It uses the number of outcomes possible in an event to determine the likelihood of that success occurring. So both experimental and theoretical probability use the same formula. The probability of an event equals the number of successes divided by the total number of outcomes. Okay, so let's look at an example. Find the probability of find the experimental probability of each event. So number one, a basketball player attempted 24 shots and made 13. Find the experimental probability that the player will make the next shot. So the probability that the player will make the next shot is equal to the number of successes divided by the total number of attempts. So they made 13. And had 24 attempts. So 13 over 24 is the answer. In my calculator, we're going to break that down into a decimal and round it to the nearest hundredth. So 0.54 is the rounded answer to the nearest hundredth. Let's look at the next problem. Another basketball player missed 10 shots and made 12. Find the experimental probability that this player will make the next shot. Okay, this one's a little bit tricky. Notice that it says that the basketball player missed 10 shots and made 12. Most people, when they do this, they make a mistake and they'll give me the fraction 10 over 12, or I don't know, something else. But it's not about just taking the two numbers that are given and just creating a fraction out of it. Instead, it is following the formula that I gave you earlier. Okay? So the probability of making the next shot is equal to the total number of makes, which is 12, divided by the total number of outcomes. Now, the total number of outcomes were 10 missed and 12 made. So 10 plus 12. So that's equal to 12 over 22. Now we can turn that into a decimal as well. In my calculator, I have the fraction 12 over 22 gives 0.54 repeating. 54, 54, 54. So this actually rounds to 0.55. Let's look at the next problem. So I'm going to leave this problem for you to do on your own as practice. And let's do the next problem as well. A baseball player. That's going to be for your own working. Let's look at examples of theoretical probability. A bucket contains 15 blue pens, 35 black pens, and 40 red pens. Find each theoretical probability. So, number one, what's the probability of reaching into the bucket blindfolded? They're all mixed up in there, and I pull out a black pen. What's the probability? Well, that's equal to the total number of successful outcomes, which would be, how many black pens are there? There's 35. And how many total outcomes are there? There's 15 blue plus 35 black plus 40 red pens. So, that denominator, 15 plus 35 plus 40, is equal to 90. So 35 out of 90 is our probability. Now we can write that as a reduced fraction. We can write it as a decimal. For now, I'm interested in just 35 over 90 and also writing that as a decimal. So 35 divided by 90 is 0.38 repeating. So if it's 0.388888, this actually becomes 0.39. Number two, what's the probability of reaching into the bucket and selecting not a blue pen? Okay, so to do this problem, you have to ask yourself, how many pens are not blue? And I see that we have 35 black and 40 red. So there's a total of 35 plus 40, that's 75, not blue. divided by a total of, we said, 90 outcomes. So 75 divided by 90 gives 0.83 repeating. So this rounds to 0.83. So I'll leave this one for homework as well, for your own practice. And now I'd like to get into compound events. So, compound events consist of two or more events linked by the words or and. You will decide whether you are adding or multiplying in these problems based on which type of compound event you have. So let's look at some details. And I think we should do that in the next lesson. So let me stop the video here, and you can catch Unit 1. You can catch the compound event or problems in the next lesson. Thank you for watching.